Hi, everyone. As site reliability engineers, having deep visibility into applications is critical for maintaining robust systems. Doing so without modifying code can be challenging. This talk focuses on Java and the JVM, but the principles apply to other languages as well. I'm an observability veteran currently at ServiceNow. Come see me after if you want to learn more about my background or discuss this presentation in more detail. Today, I'm going to talk about how OpenTelemetry can monitor Java applications, but the same concepts can be applied to other languages. Let's say your application trace looks like this with just the default instrumentation. With the concepts in this talk, you can make your traces look even richer and more detailed without application code changes. Let's get started. For those that might not be familiar, here's a definition of observability. Nobody likes to hear customers complaining about an outage or performance problem, even worse when it's something that you're not aware of. Having an observable system allows us to detect problems and react quickly and decisively when one is identified, instead of having to wait for a customer to complain or give feedback. Observability is commonly achieved through a combination of several complementary systems, like tracing, logging, metrics, and so on. OpenTelemetry is an open source project that brings together many vendors and community representatives to work on unified standards for tracing, metrics, and logging, and also naming conventions, rather than duplicating those individual efforts. Collecting this data enables an aggregate view of critical signals like throughput, response time, and error rate. Today's talk will primarily focus on tracing. The OpenTelemetry project provides common APIs and a default SDK implementation for many different languages. When writing manual instrumentation, these are the APIs that you interact with. Library-based instrumentation is also available for many languages and frameworks, and is great when you want to control more without needing to rewrite everything from scratch. When possible, the most popular languages also have automatic instrumentation tooling that enables observability with minimal effort. The JVM enables automatic instrumentation through a special Javaagent flag added to the JVM startup arguments. Download the latest version of the OpenTelemetry Javaagent and add it like this. By default, it will report data to an OpenTelemetry collector running on localhost. The Javaagent is highly configurable by both environment variables and system properties. When a Javaagent is added to the startup argument, the JVM allows it to modify class bytecode at runtime. Each time a class is loaded, the Javaagent is presented with the class bytecode. It's then responsible for parsing those bytes out, modifying them if desired, to add instrumentation or such, and returning the resulting bytes in a valid format. The instrumentation inside the Javaagent looks for specific classes to modify as they are loaded. When a target class is identified, predefined transformations are applied to the class. The OpenTelemetry Javaagent performs sophisticated compatibility checks before transformation to prevent modifying a class in a way that might break the application. It can distinguish between incompatible versions and apply the correct instrumentation for a version that's currently running. Extensive instrumentation has been developed to cover the most popular libraries and frameworks. Please reference this URL to see a full list of the supported libraries for the OpenTelemetry Javaagent. If you're using something that isn't supported, please consider submitting a pull request with instrumentation or filing a feature request issue in GitHub. Instrumentation development usually follows aspect-oriented programming principles, or AOP, which introduces advice and point cuts. Let me show you what those mean. Let's say this is a method from an application that we want to use AOP to add an authorization check. In AOP, advice is the common cross-cutting logic to be executed at particular locations. This isn't a usual method that would be invoked directly, but rather defines code to weave into other locations. The Java agent defines similar advice for each instrumentation that it wants to instrument. A point cut defines the methods or locations where an advice should be applied. Syntax varies depending on the AOP framework, but in this example, we see the point cut declaring passport check advice should be applied at the beginning of the attend SREcon method. AOP point cuts can target other locations too, like the end of a method, field access, or a specific method invocation. With the advice applied, our method now looks like this. You can see the green showing where that advice was added. In many distributed systems, this logic might be taken care of by an application or API gateway, but here we're adding the check directly into the application code. The result is the same, though. We have encapsulated the auth check in a way that doesn't interfere or commingle with the application business logic. AOP can be useful anytime you wish to apply cross-cutting logic, such as logging, security, or observability in a consistent way. While most OpenTelemetry advice is specialized for each framework, the OpenTelemetry Java agent also defines a generic advice that can be applied to arbitrary methods for timing the invocation and capturing exceptions or other attributes. This generic advice is great to fill in trace gaps and add visibility to important methods that out-of-the-box instrumentation doesn't cover. Point cuts can be defined to apply this advice through a method annotation or configuration. If you have the ability to modify your code, the annotation should be preferred since configuration-based point cuts can break. For example, if the underlying class is modified through renaming the package, class, or method name, the configuration would also need to be updated to match. On the other hand, configuration can easily be updated without recompiling, so there are trade-offs between the two. Finding methods to instrument can be challenging on unfamiliar code bases. I wrote a tool to help identify candidates and provide configuration that you can use to apply and instrument them. Let me introduce you to Flashlight. Flashlight is a command line tool that scans a code base and displays candidate class and method names for instrumentation. These methods are identified using some heuristics that I'll talk about in a minute. The output of the tool is already in a format for configuring the OTel Java agent. Flashlight can be found on GitHub at this location. Feel free to check it out later. To get started, download the latest release here. And then let's do a quick demo to talk about how it works. In this demo, I'm going to use the popular Spring Pet Clinic project as an example, but any project that compiles to Java class files should work. Here I've already put Flashlight in the downloads folder, so let's navigate to the project's code base. Pet Clinic is a Maven project, so we can run the Maven compile task to make sure that it's ready for Flashlight to scan. Once that's done, you see the compiled classes in the target class folder. Flashlight is distributed as an executable jar. So we can make sure that we can run Flashlight from our project directory by calling java-jar and the path to flashlight.jar. The default command shows all the command options. We'll discuss a few of these later, but for now, notice the output guidance on how to run with Maven and Gradle projects. As we saw, Pet Clinic is a Maven project, so this is the command we want to run. Running it again, with the target class directory added, Flashlight scanned all of the compiled class files and identified some candidates for instrumentation. I can take the system properties or environment variable block at the bottom, remove any methods that might be concerning, then add it to my configuration for my application. These methods will be instrumented the next time I restart. I'll talk more about this in a bit, but I want to emphasize that you should review the entries here before applying the config. Blindly copying and pasting might result in something being instrumented that shouldn't be. If the resulting list is too long or too short, I can adjust the heuristic thresholds with these command line options. Different code bases and coding practices can change what is deemed useful for these thresholds. So figure out what works well for you and your application. You probably have some ideas based on the section names here, but let's talk about the heuristics Flashlight is using to identify these methods. In order to be useful, the heuristics attempt to distinguish between methods that are useful to show in a trace versus those that are likely to be performance sensitive. This is not possible to determine statically, which is why you must review the results and ideally test before running in production. The first heuristic identifies methods with locking or synchronization. Something I want to emphasize is that locking is not always slow and can be risky to instrument, but it is a useful indicator of something that is potentially important. Next, it attempts to identify methods that call networking clients. The approach here is to scan each method invocation and look for calls to classes with a name ending with client or repository. These methods are usually blocking on network I/O, so likely a good candidate for instrumentation. But if your application is asynchronous, that might be problematic. Notice we're not trying to instrument the underlying client or client method, but rather the caller that's invoking the client. Hopefully the client itself is already instrumented using the out-of-the-box instrumentation, so this should just help add some context. Finally, we count the number of method calls and branches. Using the thresholds we discussed earlier, methods with a higher number of either of these values are worth looking into. Reasonable thresholds depend on the code base, but if the resulting output is overwhelming, you can increase the thresholds. Likewise, if you feel something is missing that should be there, feel free to decrease them. The heuristics here are a work in progress and will benefit from broader use and feedback. If you have any other heuristic ideas, I'm happy to chat afterwards. Please come and share. For example, maybe disk I/O would be another useful signal for something to instrument. Now let's talk about a few guidelines when choosing where to instrument. First, keep the number of spans manageable. Generating too many spans can degrade application performance and increase observability costs. Complex distributed systems should have spans per distributed trace in the tens or hundreds, not in the thousands. Focus on your business code. This is the area that is most meaningful to you and your developers, and unlikely covered by existing instrumentation. Let the automatic instrumentation cover the standard open source frameworks. Next, when viewing existing traces and you see a big gap, try to identify what that gap represents and add additional instrumentation to fill it for next time. It's much better to do this before an incident occurs rather than in the middle of one. Business logic often has critical branches that can dramatically change the behavior of the application. A common example of this is a feature flag that you use to gate a new feature. Ensure you have visibility for this in your traces to help understand application behavior when trying to troubleshoot. Sometimes it's better to add attributes to an existing span instead of creating a new span. Doing so without modifying your application code is a bit trickier. Similar to the @with_span annotation we talked about earlier, the Java agent has a @span attribute annotation to capture method arguments as a span attribute for the current span. There isn't a configuration-based analog, though, so if you can't modify the code, writing an extension is your best bet. We'll talk more about extensions in a bit. Adding attributes are a great way to extend and customize existing instrumentation without needing to rewrite it or generate additional spans. Many tracing backends also allow you to search or filter by these attributes, which is great for finding commonality when troubleshooting a problem. Attributes like these are helpful in understanding the scope of a problem. For example, which user is causing a particular error, or what impact a regression is having on enterprise tier customers. You can use attributes to help identify those questions. One thing, cardinality is important to consider when adding attributes. Traces are generally not sensitive to cardinality, but metrics are. So if an attribute is being added to a metric directly or indirectly from a trace, be very careful to ensure that the cardinality of that attribute is constrained. Now let's talk about what to avoid instrumenting. Adding instrumentation to a method that is already instrumented can have unpredictable results as the order of instrumentation is applied within the OTel Java agent is not guaranteed. So it's better to leave methods that are already instrumented alone. Next, don't overdo it. Adding a span for a method that executes in less than a millisecond is probably not going to offer much insight when triaging an incident. This especially applies for methods in a tight loop. Instrumentation can degrade application performance. Finally, consider testing instrumentation changes in a pre-production environment to ensure that it doesn't cause performance or other problems. As I alluded to before, OpenTelemetry Java Agent has an extension mechanism that allows additional classes to be loaded with and utilized by the Java agent. This enables you to extend the Java agent without the need to repackage everything together. Extensions are much easier to maintain since the extension and Java agent are packaged separately, so staying on the latest Java agent doesn't require rebuilding the extension every month when a new Java agent version is released. If for some reason you need a single file Java agent deployment, tooling does exist to enable that. Common use cases for extensions include programmatic configuration, custom SDK components, like a sampler or exporter, and custom instrumentation, for example, to add attributes or metric collection. If the Java agent doesn't do something that you want it to, there's a good chance you can make it work with an extension. Finally, if you already use AOP tooling in your application, you can also use those tools to add custom instrumentation instead of an extension. Other AOP tools apply instrumentation in different ways. For example, Spring likes to make heavy use of proxy objects that wrap and delegate to the original object. ByteBuddy can dynamically generate classes on the fly. I also want to briefly mention profiling as an excellent complementary way to get visibility into application behavior, especially if you're trying to optimize a CPU-bound task. The reason I say complementary is because it shows an aggregate view across many requests, so outliers may be difficult to identify. In contrast, traces are unaggregated and great to understand outlier behavior. OTel contributors are actively working on unified profiling project, but don't have anything for us to try just yet. Meanwhile, these are some great projects that you can try. They are used as the core of many profiling tools, so they already have wide adoption. Brendan also has published some great material on the subject of profiling if you want to research more. Thank you for coming to my talk. I have a couple minutes for questions now, or you can see me after and we can discuss things in more detail. Thank you.